In this video, we'll be discussing the principle of conservation of energy along with a handful of applications of this principle of conservation of energy in our society today. So recall from our last video that we defined conservation of energy as being the principle that energy is never created or destroyed. Energy can be converted from one form to another, but it cannot be created or destroyed from nothing. It's always there. It's just moved from one type of energy to another. If we add the total energy in the universe, that amount of energy is constant. That number will never change. Here is a figure from your textbook that talks about a few of the different types of energy conversion processes, going from one type of energy to another and the type of process that would cause such a conversion of energy. Let me give you one very realistic example that we deal with every day. Here is an example of, say, a person walking around outside, riding a bike even. Energy, first of all, starts off as a nuclear reaction within the sun. And then that nuclear reaction converts nuclear energy into radiant energy in the form of visible light. That visible light is then absorbed in the tree through a process called photosynthesis, which we have here in our graph. And then the plant life grows and then is eventually consumed by human beings. So it's just converted from one form of chemical energy to another form of chemical energy. And then that chemical energy is converted into mechanical energy. This is what we would call a heat engine. The person who has this chemical energy starts transforming the stored chemical energy into motion. Well, then after that, say the biker applies the brakes, there is friction involved. Friction is the process moving from mechanical to radiant energy. In other words, you heat up the wheel due to the friction of the brake, and that heat is emitted, probably in the form of infrared radiation. So that is a good example of energy being converted from one form to another, a whole process. And by no means did it actually ever start with a nuclear reaction, nor did it end with radiant energy. That process goes on forever in both directions. So if we look at the types of energy used in our society today, here's a graph that shows the different types of energy. When we began many millennia ago as a human species, we primarily used wood being a type of renewable resource. Eventually, we realized that coal was more efficient, so we converted to coal. Now we use primarily petroleum. And so you can see that as society changes, as industry increases, we change from one form of energy to another. So currently today, 35% of our energy is derived from petroleum, 18% from coal, and 28% from natural gas. All three of those are fossil fuel-based energy sources. Of the energy sources that we use, about 89% can be traced all the way back to photosynthesis. Wood is obviously plant life, which needed photosynthesis to grow. Coal is decayed tree life that has been under high pressure over many thousands of years. So it is tree life, formerly tree life. Petroleum is animal matter that has been under high pressure and temperature for many thousands and millions of years. But where does animal life thrive? In the consumption of plants, which needs photosynthesis. So you can see how important this photosynthesis process is in almost all types of energy. Probably some of the very few exceptions would be nuclear power, solar power, which is under renewable, wind power. Those types don't require photosynthesis. But all the others, especially the primary ones we use today, photosynthesis is key. How do we use this energy? Primarily, a third of the energy we use today is used for heating, or cooling for that matter, air conditioning or furnaces. And about 2/3 of our energy is used in engines and generators, such as automobiles and electricity generation. And you get the general idea. Let's take a quick look at a few of these different types of energy sources. We'll start off with petroleum. Petroleum is oil from any type of rock that, well, contains oil, an oil-bearing rock. Petroleum comes from organic sediments that are transformed over time under high pressure and temperature by bacteria. So you have animal life that dies, bacteria transform it from one form to another, but being under high pressure and high temperature, it causes all the material from the animal to decompose and form into oil, which we call petroleum. Natural gas is a derivative of petroleum, a very similar process of forming it, but instead of being a liquid form, it is gaseous form and is generally produced at higher temperatures. When we mine petroleum, harvest petroleum is probably a better term, natural gas is often found with it. They are often associated with each other since the processes come from the same sources and have the same process of development. Our supplies of petroleum are unfortunately quite limited. Many of our supplies are offshore, and even more, about half of our supplies are imported from other countries. Coal is another energy source, very similar to petroleum, but coal is accumulated from plant material processed over time by high pressures and high temperatures. Unfortunately, it's not pure plant life. We would hope that coal is nice, pure substance, but it's not. You get ash and minerals and gases and other chemicals that are embedded inside of the coal. We call these impurities. And then when the coal is burned, these gases and impurities are either released or they react within the combustion reaction and produce a pollutant, such as sulfur dioxide. So petroleum, natural gas, and coal, all three of these are known as fossil fuels because they are derived from fossilized plant and animal life. Here's another way that we can generate electricity, any type of energy really, but not from fossil fuels. This is from moving water. Right away, the term moving makes us think it has kinetic energy, because that's what kinetic energy is. It's the energy of motion. And the cool thing about this type of energy is that it's renewable with rainfall. Whenever you have rain, you resupply your water and you renew your energy supply. Basically, what we get is gravitational potential energy. You have, say, a reservoir full of water, and there's a certain height of that water up above the base of the dam that's on the edge of the reservoir. So you have gravitational potential energy because of that. Then as that water falls, the potential energy is converted to kinetic energy, which is then converted to electrical energy. Currently, about 3% of U.S. total energy consumption comes from hydroelectric power plants. We would love to have more. However, unfortunately, the resources, the growth potential is quite limited by the decreasing availability of new sites. You have to have good potential where there's a constant source of water. You have to have a place where water can build up, so on. There are a number of things that you need for hydroelectric power. And so the number of available new sites has been decreasing. Nuclear energy is another, well, rather splendid, honestly, method of energy production. Yes, it's controversial, and yes, it can potentially be dangerous. Just a little caveat here. Honestly, any type of energy production is dangerous. Any type of energy production will cause harm of one form or another in the worst case scenario. Now, back to nuclear energy. That was just a caveat. Moving on, based on the textbook, there are two types of nuclear energy. There's fission, which is the splitting of atoms, or fusion, which is taking two atoms and joining them together to make one atom. Good example of fission would be taking a uranium or a plutonium atom, and they split into two smaller atoms. This is the process that we use today, and unfortunately, it produces a substance that is radioactive, quite a bit of radioactive waste, which is a challenge. The other problem with fission is that you get chain reactions. The idea of fission is you have an atom which releases 3 neutrons. Each neutron will then impact another atom, which causes it to decay into 3 more neutrons. And you can see this process continuing over and over and over until basically you have an uncontrolled reaction. This would be worst case scenario. This would be an atomic bomb. So the idea of a fission reaction is basically stop 2 of those neutrons from forming, which means all of these reactions don't happen. And then you have another reaction, you stop two of those reactions from happening, none of these happen. So you can see that the total number of reactions decreases significantly, thus producing a more stable reaction. That is a nuclear power plant. However, if something goes wrong, the chain reaction starts all over again, and you can potentially have a disaster. One reason why this is a controversial issue. Fusion, on the other hand, takes 2 hydrogen atoms, 2 very small atoms, creates helium. The 2 hydrogen atoms are squished together to form 1 atom of helium. Now, the cool thing about this process, nuclear fusion, is that once that process is done, it's done. It doesn't create a chain reaction, so it will not go out of control. There is no nuclear waste, no radioactive waste. It's a very, very clean energy source. In both fission and fusion, the process of generating electricity is that you have a nuclear reaction, either fission or fusion, and that's going to release a lot of energy, which is absorbed by water. The water is heated in the reactor and turned to steam. The steam then is used to turn generator turbines. This process is exactly the same as fossil fuel-based electricity generation. You burn coal or petroleum to heat water, which evaporates, turns a turbine. Hydroelectric, we already saw that a little bit. Many different, even some solar power plants use the same processes. So the basic process is the same, just where the energy is derived from, it comes from nuclear energy. That's what makes this one unique.